again. I must thank the organizer very much for giving me the opportunity to come back to Korea and to Kias that I like very much. So now what I'm going to talk about is very linked with the talk by Rita Pardini, but I'm going to focus on the irregular surfaces. Also, I must excuse myself with the experts on irregular surfaces that are here, because I'm going to start with somewhat more elementary facts, because part of the audience is not such experts on irregular surfaces. So just to define the setting, I'm considering a smooth algebraic projective surface over C. PG is PG, and the irregularity is H1 of OS, H0 of omega 1. And S is irregular if Q is bigger than 0. And when Q is bigger than 0, we have an additional tool to deal with surfaces, with irregular surfaces, and that is the Albanese map that I've defined there. So as Rita already explained, we say that S has maximal Albanese dimension if the Albanese map of S is generically finite, and S has an irrational pencil of genus, we say an irrational pencil of genus B of S is a map with connected fibers, with B a curve of genus B bigger or equal than 1. I'm not following Rita's, because I prefer to say genus B bigger or equal to 2 when the surface is not of maximal Albanese dimension. What happens is that this map from S to Albanese of S gives you a fibration of S over a curve of genus Q. And and now what happens with irregular surfaces is that somehow the existence of one-forms, global one-forms on them, restricts more their invariants. The first general thing is that for irregular surface we always have PG bigger or equal than 2Q minus 4. But in fact the equality cases are completely understood. So equality holds, then S, if minimal, is just the product of a curve of genus 2 and a curve of genus Q minus 2. So this was, I don't know, I mean, this complete characterization I've seen in Beauville. Probably it has been done before, I'm not sure. I
try to remember.
Okay, this is
some Belgian mathematician, Youngmans.
Huh? Youngman?
I think.
No. Youngmans was doing things about Castelnuovo, 3pg minus 7, I think. K squared bigger or equal than 3pg minus 7 for the canonical map. I think that's yours, Youngmans. I think this one, Beauville obtains it as a elaborate corollary of Arakelov's theorem and so on, but I'm not sure. This is in this appendix of de Barre's work. I don't know whether it was known before. So,
I think it was Youngmans.
oh, maybe yes. Okay. Now. Of course, when we have this PG bigger or equal than 2Q minus 4, and we know exactly what is when PG is 2Q minus 4, then natural question is to understand what happens if PG equals to Q minus 3. And here, if the surface has an irrational pencil of genus bigger or equal to 2, an irrational pencil in Rita's notation, it's possible, there's a complete classification, precise description how they look like. A great part done by Barga, Naranjo, Pirola, and then we just picked their calculations and showed it happened. So, and now we have the other case to consider that. Huh?
Oh, you're taking.
Sorry?
With an irrational pencil.
With an irrational pencil. By the way, something I forgot to say, the existence of an irrational pencil of genus bigger or equal to 2 is detected by the fact that 2, 1 forms wedge to 0. Okay. Then I think Pietro also told about this. If PG equals to Q minus 3 and S has no irrational pencil of genus bigger or equal to 2, then we also, what do we know? For Q equals 3, it's known by work of Akan, Pardini and Pirola at the same time, that S is the symmetric product of a curve of genus 3. If Q equals 4, we know that K squared is 16 or 17 by work of Barja, Naranjo, Pirola and Cousin Pirola. Very beautiful things, and there are the examples that the only examples we know are, probably the only examples that can exist are these of Schoen that Pietro described this morning. For Q equals 5, there are no such surfaces. And if Q is bigger or equal to 6, no example is known, but we know several restrictions on the invariants, on the geometry, on the behavior of the canonical map, and so on. But I don't know. I personally think probably they don't exist. But I don't know, and we have not found a good argument yet. So that's okay. Another restriction that irregular surface has is if it has maximal Albanese dimension, then K squared is bigger or equal than 4K, which is very different for for surfaces of general type that are not irregular. We know that K squared is bigger than 2K minus 6, so this is quite far away. This is severe inequality that was proven, thought to have been proven by Severi, and then I don't know really the story. So I think Fabrizio then found. What did you do? You rediscovered this?
He didn't prove.
He didn't prove. I know. It stated in but he gave a wrong proof, right? Or
yes, he claimed that every mapping to an abelian variety is unramified.
Ah, okay.
Okay.
Oh, that was.
The argument proved that the mapping has no ramification.
Okay.
So it's a local invention.
Anyway, I grew up hearing about this Severi conjecture, and then finally it was proven by Rita Pardini in 2004 with a very, very ingenious method that I advertise.
Severi, surfaces with Q equal 2 don't exist. general type
Okay.
with maximal Albanese dimension, because the mapping to the
It should be ramified.
is unramified, and so it's a torus.
Okay. Okay, I see. I see. I never read Severi, so. Actually, there is a conjecture by Miles Reed and Manetti that if Q is bigger than 4, then K squared should be bigger or equal than 4 chi plus 4Q minus 12. Rit and I did some work about this, but we proved something towards that, but under the hypothesis that KS is ample, and the methods we used need that, and in fact these proofs accept the Severi inequality, but the proofs of all these results I was telling about need a lot of knowledge about linear systems on these irregular surfaces, fix the base loci of the linear systems, and so need to understand very carefully what curves can be in a irregular surface. So it's important to understand the special properties of curves in irregular surfaces. And that's what I'm going to discuss today. I want to discuss several things, 3 things. Curves such that the Albanese image of the curve does not generate the Albanese variety of S. I want to discuss what happens with curves that move linearly, that you had already a hint, or you heard already about it in Rita's talk. And I also want to discuss curves with self-intersection positive that do not move linearly, to understand whether they deform algebraically or not, whether they move algebraically or not. So let's start with the first thing. So, okay, so I take any curve on my surface S. I have the Albanese map, and I can take the abelian subvariety generated by the image of the curve, and we define this Albanese defect of the curve as the codimension of this abelian variety, and we will say that the curve is Albanese defective if the Albanese image of the curve does not generate the entire abelian variety. So, and now here we have a result about and now what happens for Albanese defective curves is that the intersection with the canonical divisors has a bound. So let me state the theorem. So the theorem is that if I have an Albanese defective curve, if this Albanese defect is bigger or equal to 2, then necessarily the intersection of the curve with the canonical divisor is lesser than k squared minus this Albanese defect. If the Albanese defect is 1, then we have a bound on k dot c in terms of for k squared plus the geometric genus of the curve, and in that case we will have a fibration C is a component of a fiber, of a fibration of my surface over an elliptic curve. So, but anyway, we get a kind of uniform bound for this. Let me just tell you very quickly the idea of proof. I'm not going to do the details. So, first thing, okay, this curve, the image of this curve does not generate the whole abelian varieties, so I just take the quotient and I consider a map, the induced map from my surface to this quotient. This map that I call I prime is a non-constant map, but it contracts the curve C to a point. So, in particular, we find out immediately that the curve must have self-intersection less or equal to 0. And then, in case, so now we have this dichotomy between the for the Albanese defect bigger or equal to 2 or Albanese defect equals 1. So if the Albanese defect is bigger or equal to 2, then we have two possible cases. Either the image of A prime is just a surface, and in that case C is contracted to a point, so we take when we take the pullback when we take the pullback, we find that C will be part of a canonical divisor, and we get the C is in the ramification of this map, so C will be part of the canonical divisor of S, of a canonical divisor of S. And we get, and then we get K, with a bit more work, we get the inequality, which was Ks dot C lesser than Ks squared minus this defect. And otherwise, if the image is a curve, this curve must have genus at least 2, because it generates an abelian variety of dimension at least 2, and then it's enough to and C will be contained in the fiber of this fibration, and then one uses just numerical inequalities from Arakelov's theorem. K squared is bigger than 8 times the genus of the fiber, times minus 1 times the genus of the base minus 1, and one gets the inequalities. Now, where is the big problem? The big problem is this Albanese defect is 1. Because in that case, we just have a fibration onto an elliptic curve. And unfortunately, one could think that we would like to do like before, but these inequalities for fibrations of elliptic curves don't tell us a great thing. So then one has to do a careful study of properties of fibrations, of how the fiber that contains this curve looks like, and then one gets the other inequality. So, okay, this is that's not interesting. So,
what was the star?
The star is the technical. The star is a technical lemma that's here. It's no, because I mean the main I will otherwise I want to be able to. So okay, we'll read the star. The star is okay. So the read. Huh?
No, stavo dicendo che se ti levi il foulard si mette solo nel microfono.
Allora, no, so this star is so this star is, this is the technical lemma that we needed. Somehow is this and another small argument that uses the fact that k squared is bigger or equal than 4 chi. It was is the technical heart of the thing, but it's just a simple, okay. So some comments. These results here, there's no hypothesis about the Albanese map, so it could be image curve or surface, no problem. This I've already said, c squared is always less or equal to 0. The other interesting thing is that the bound, this gives me, because this was in terms of the geometric genus of the curve, the bound that I can go back. This was in terms of the geometric genus of the curve. So this means, so we have a bound in the difference between the arithmetic genus and the geometric genus. So somehow, in terms of the number of singularities that the curve can have. And okay, this theorem sharpens result of Miyoka and Lu, general one, about again the intersection of a curve with in terms of the geometric genus and inequalities between and this term 3c2 minus k squared. And okay, and now the point is that Albanese defective curves, any curve that has geometric genus lesser than q is necessarily Albanese defective. The Albanese image cannot generate the whole, and so we get a statement, a corollary, immediate, that for curves with geometric genus lesser than the irregularity. And this also, so I just leave you to read the statement. So this gives you an uniform bound for the intersection with the canonical divisor for curves with geometric genus lesser than q. This also generalizes the result of Lu for curves of geometric genus less or equal than 1 for irregular surfaces. Okay, can I? Okay, no, let me. Okay, so there were more corollaries, but I'll skip them. So now having these curves, so in particular curves of geometric genus lesser than q have self-intersection less or equal to 0, cannot move. And now I go to the other way, that's what about curves that move linearly? And here we had, you heard in Rita's talk this morning, this inequality by Xiaogang that says if we have a curve that moves in a linear system of dimension r, then we will have always the arithmetic genus of the curve bigger than 2q minus 2 plus r in surfaces of maximal Albanese dimension. So in fact, in particular, we get that any irreducible curve that moves linearly has arithmetic genus bigger or equal than 2q minus 1, but in fact maybe this particular curve doesn't have genus, geometric genus bigger or equal than 2q minus 1, but the general curve in the linear system will have 2q minus 1 or 2q minus 2 plus r. Okay, and also this theorem tells us if equality holds, this C is a linear pencil. And maybe you remember this morning there was also involved, there was also the dimension of the tangent space to omega CS. So if we have no irrational pencil of genus B bigger than 2, then we know that the dimension of the tangent space to omega CS is 0. So this will be, I think it would be interesting to classify, to understand when you can have this exactly this situation, a system of curves of geometric genus 2q minus 1 moving. Okay. So, I think Rita explained well this morning, but here an essential tool to prove this inequality is this fact that the restriction map from K to D has image of dimension bigger or equal than q minus 1. This is essential, and it's true as long as my divisor or curve is not contained in the ramification divisor of the Albanese map. Okay, so that's about what I wanted to say about curves with that move linearly. I'll stress again that I think this would be a very interesting problem to understand. I don't think I really don't think I know. Maybe there's some example. Okay, and now I wanted to discuss also exactly curves that don't move linearly. Okay, so there are cases, immediate cases that cannot move linearly, which are the irreducible curves with self-intersection negative. What I want to see is exactly what happened. So I just recall from this morning these Brill-Nutter locus, omega 0 in this case. I'm taking curves with H0C equals 1. So I'm taking some irreducible curve with H0 of C equals 1. In this case, I wanted to understand the behavior, the deformations of the curve. So I want to consider the tangent space to 0 of omega CS, and here because H0 of C is 1, and because of the theorems Rita was explaining this morning about the structure, in fact we have that H0 of C restricted to C is isomorphic to T, so we can control the dimension and so on. So in particular, if H0 of C is restricted to C is 0, the 0 in the Brill-Nutter locus is an isolated point with reduced structure. So, and this will happen, for instance, fixed component. No, that second one is, huh?
You just said the tangent space is natural isomorphic to H0 of C.
Sí,
Okay, so
because of this map.
that is 0, okay.
Yeah, but you need to, okay, you need H0 of C equals 1 so that you can identify this with the map of H1 to OM, so on. Okay. Did I? Okay, no. This we can find out more things about these curves using again the general results from this morning that I here translated, where concerning again the restriction map from KS to an effective divisor. So I translated. So the results this morning that Rita stated in all generality for the varieties of dimension n say that if we have a surface with no irrational pencil of genus B then 2, and we have an effective divisor that doesn't move, and the dimension of this tangent space is bigger than 0, then we know that the image of this restriction map is in fact what's stated there. If D is not contained in a canonical divisor, this will be bigger or equal than 2q minus 3. If it should be anyway, but if D is contained in a canonical divisor, then the rank again of this image would be will be q minus 2 plus dimension of T, or 2q minus 3. So which is a bit bigger than q minus 1 in general. So okay, and this dimension of T bigger than 0 means exactly H0 of C restricted to C bigger than 0. The dimension of T is just H0 of C restricted to C. So if we play around with the previous proposition and use just Riemann rock on the curve, we find out some inequalities between C squared and K dot C. So there's yes, so if this tangent space has dimension q, then we find out that C squared plus 2q minus 6 is lesser or equal than K dot C, and if it's lesser than q minus 1, then C squared plus 2q minus 4 is lesser or equal than K dot C. So this proves
What is the
hypothesis.
How do you use the proposition?
Because I have these ranks.
No,
So the next proposition I use nothing. I find these inequalities. If my curve moves algebraically, my curve it doesn't move linearly. It moves algebraically. Then I know there are these.
The estimate is more or less the same. Yes.
Which estimate? Okay, why did this come like this for q and q minus 1? Because of these two these estimates come from Riemann-Roch applied to H0CC and H0K restricted to C, just Riemann-Roch on the curve. And they are a bit different because also the theorem is a bit different when dimension is less or equal to q minus 2 and bigger or equal than q minus 1. Okay. Huh? Okay, so the proof uses previous proposition, Riemann-Roch, adjunction formula. Okay, so this is just... okay, now this expression c squared plus 2q minus 4 lesser than ks dot c can be rewritten in this way. Q minus pa of c plus c squared less or equal to 1. I can make the calculation, but and this is exactly the Brill-Nathan number discussed this morning, right? And now sorry?
Rho C was the Brill-Nathan or what?
Was the Brill-Nathan number, yeah. This is Q. Q is the dimension of peak 0s. Huh? And
Except that Brill-Nathan was for curves.
and this is a curve.
The Brill-Nathan number was for linear series and curves.
No, but then there was a Brill-Nathan number for the divisors on n dimensional variety.
Yeah,
On surfaces, yes. The Brill-Nathan was for curves on surfaces, right? So, and there was this theorem that I translated. This was only for surfaces. So that gave us this existence theorem that tells that if this Brill-Nathan number is bigger than 1, or it is 1 and the curve is not in the ramification locus of the Albanese map, or it is 1 and the peak 0 is not generated by the Green-Lazarsfeld locus, then this Brill-Nathan locus has an irreducible component containing 0 of dimension minimum between Q and Rho. Right? Okay? So we can apply. So now we can apply this to something. So if H0 of C is 1 and C squared is bigger than 0 and H0 of C restricted to C, we know that dimension of T is 0. So if the dimension of T is 0, okay, by the previous theorem, we must have that Rho of C is less than less or equal to 1, because otherwise 0 lives in a component of dimension positive dimensional. The tangent space cannot have dimension 0. So necessarily Rho of C is less or equal to 1, and we find also for the curves where this tangent space is dimension 0 an inequality, because this inequality was needed that this tangent space has dimension bigger than 0. And now, so now we find here also the equality, the same inequality for dimension 0, and also if we have equality, then It means rho of C is 1, so we have at the same time that the curve is in the ramification locus of the Albanese map, and that it is one of these very special cases where V1 generates. Okay, so now okay, these curves that do not move and have c squared bigger than 0. This is bigger or equal. No, bigger or equal to 0. So by the shell result, curves that have arithmetic genus less than 2q minus 1 cannot move linearly. So the previous results will apply to any curve with c squared bigger than 0 and arithmetic genus lesser than 2q minus 1. Are there examples in this range? Yes. You take just curve in the symmetric product. This gives you a curve with arithmetic geometric genus equals q, one of the coordinate curves. So, and c squared equals 1, and everything before applies. But in fact, this is something I'm not going to discuss, but in fact, when we have on a surface, irregular surface, one connected divisor with self-intersection positive and arithmetic genus equals q, there are no, if the surface is minimal, there are not many hypotheses. Either the surface is a product of curves, and this divisor D is just the sum of one fiber from one side with the fiber from the other, or the surface is a symmetric product. This is a very miraculous result, but it's like that. It's a bit atypical, because usually you cannot tell what surface you have if you just know one curve that lives there. You can sometimes, well, with rational surfaces, but except that you don't, if I give you a curve, you don't, but here it's, but anyway. Okay, and this was, in fact, we looked very hard for curves in this range, so that cannot move, and have c squared bigger than 0. And
if they, you're assuming
what?
So you're saying the plane is also symmetric product?
Oh no, for surface of general type. I think we were.
I think the plane is a symmetric product of P1.
Yeah, probably it
So
can.
was,
Okay, no, but okay, we did. No, we assumed general type, but possibly we could. No, I don't know. I don't remember, but possibly we could do away with the hypothesis of general type. But to be frank, we were not so interested in. Okay. So, but this was the only example. Now, and I must say, we even, at least I did. I can't swear for my co-authors, but at least I kind of was convinced possibly it was the only possible example. But Mary Saez, who is a student of Barja in Naranjo, just constructed an example of such a curve with genus 9 inside a symmetric product of a curve of genus 6. So this has Q6, so it's a curve in this range. So, and hopefully, possibly, if her method works, a lot more will be found. Of course, I would like So I think I have not time yet to really look at the thing, at the construction, but anyway, I would like very much to find also other examples, because one big problem in all this theory of irregular surfaces is that in a certain sense we know very few irregular surfaces. So with vibrations it's not so difficult to find them. But these ones, and the maximal Albanese dimension, we can also, it's not also so difficult to construct complete intersections in abelian varieties and so on. But then if we start looking more, what do we have? Products of curves, symmetric product of curves, the Fano surface, which is a fascinating one. This example of Schoen, that it's also very fascinating. But we have a big lack of examples also, to understand how, like pathologies of the canonical map, of the ramification divisors, and I don't know, maybe this Gorenstein smoothing could be used, I don't know how, but to find other examples, because in fact one would imagine we should know many more, but it's not. There are many mysterious things. Okay, and again, we can say something. Okay, this is again the same things, but we can also, again using Riemann-Roch and these results before, find what is the codimension of the tangent space for such a curve. When I take this range, curve has arithmetic genus less than 2q minus 1, the curve does not move. And using the, okay, let me go back to the theorem I should have put. Okay, using this theorem that gives us these ranks of the restriction map of the canonical divisor to the curve with the dimension of t, then we can find also restrictions for the self-intersection of the curve. For instance, in this case of I was telling about the symmetric product, we have PA equals Q, so any such curve would have to have C squared equals 1, a irreducible one. And if PA is Q plus 1, C squared is necessarily less or equal to 2. And we also know how much we have a bound on how much it can move algebraically. So, yeah, okay. The first statement gives C squared less or equal to 2. Why is it here? Because before we had these more general theorems. We had with great effort proved that C squared was less or equal to 4, I think, or 3, but with great effort, very lengthy proofs. And then with these, yeah, statement 2 can be looked as a kind of generic vanishing. Yeah, and the idea of proof is again we must have rho of C less or equal to 1 because then and then Riemann Roch, line one, well, yes, all that. Okay, and maybe now I'll go very quickly about some related results. Okay, so I think I've finished with the numerical inequalities for this, but now the same kind of methods. Well, I don't think Rita mentioned this. No. In fact, we could also give a statement about the fixed part of the paracanonical system. I don't think lots of people here are so familiar with paracanonical system. So, paracanonical system of a surface is the connected component of the Hilbert scheme of S that contains a canonical curve. And we have a natural map from this paracanonical system to peak zero, given by just taking the class of a curve to C minus K. And there is one component that dominates peak zero, exactly one. This is the main paracanonical system. Paracanonical systems have been used with great effect by Fabrizio and Ciliberto to classify like surfaces with PG equals Q equals 1, K squared equals 3. This was with a very, very nice thing. And there is, yeah.
Okay.
No, there's nothing else.
There's nothing else.
No, it was just, I didn't notice, I should have put this, okay. And in a certain sense, something about the paracanonical system. The main paracanonical system is understood. This is work of Beauville in the 90s. So if we have no irrational potential of genus Q bigger than Q over 2, then we have a different behavior according to whether Q is even or odd. If Q is even, the complete linear system, canonical system, is a component of the paracanonical system, so general canonical curve is not in this main paracanonical system. If Q is odd, the behavior is the general canonical curve as the first order deformation to a paracanonical curve. We don't have an obvious relation between the fixed part of this paracanonical system and the fixed part of the canonical system. But if S is maximal Albanese dimension, the fix, we know that the fixed part of Ks is always contained in the ramification divisor of the Albanese map. It may happen that not every component of the ramification map has to be in the fixed part, but the other way, yes, because and in fact, with again the same so the same kind of methods, we can prove that a curve with self-intersection positive that is in the fixed part of the paracanonical system is necessarily in the ramification divisor of the Albanese map. So this is it's again all the theory of the Brill-Noether loci. And okay, and now I couldn't resist. I'll finish with this. I've put something on the statement for n-dimensional because neither Rita or Pietro mentioned this. And so, okay, so in general, for dimension n, it's also true that the fixed part of the canonical system is contained in the ramification divisor for n-dimensional varieties of maximal Albanese dimension. And the point, okay, and now for the ramification divisor, again the same type of methods. We showed that any subdivisor of the ramification divisor, this map from H1 of OX to H1 of OXZ induced by cup product by a section that defines Z is injective. And this, in exactly the same way I was saying before, means that if this divisor Z does not move, then in the same way, 0 is an isolated point in the Brill-Noether locus with reduced structure. And this has a corollary that for any dimension, but in particular for a surface, that any divisor in the fixed part of the canonical system cannot deform, so it will be isolated in the. So that's for maximal Albanese dimension, which is again, I mean, I think even the fixed part of canonical systems are still mysterious, so it's a little, and that's it. Okay, but this is, since this was general, I just put it. So I think what? Huh? Well, I don't think. I think I can finish here. So.